Okay, so we're back for the second part of hypothesis testing for standard deviation, and while we were gone, it seems that dinosaurs took over. So at least the Brontosaurus thinks that math is fun, and the Indominus Rex says that he likes pie. Okay, yeah, so dinosaurs, Blue is the favorite dinosaur in this house. Indominus, Brontosaur. Okay, we'll move you to the side. Okay. All right. So, let's get back to this lecture then. So in the first part, we talked about using the calculator in order to do chi-square tests, to find chi-square areas and stuff. So we're actually ready to jump right into the standard deviation problem. Okay, so let's go ahead and do that. Let's see what we got here. Now again, first example made up, second example made up, all examples today are made up. Okay, so remember when we talked about this, that standard deviation is very technical, so these problems are a bit more technical than what we've seen in the past. So this says a potato chip bagging machine puts 16 ounces per bag. That's too hard with this pink pencil. Let me find another one. The standard deviation is set to 0.4 ounces. The quality control manager thinks the bags vary too much in size. A sample of 14 bags finds a standard deviation of 0.47. Test the claim at alpha equals 0.05. Okay, so as I said, a bit more technical in this problem than what we're used to seeing. So we're talking about bagging potato chips, and the potato chip bagging machine is set to put 16 ounces per bag. But like we said, that doesn't mean that every single bag is going to be exactly 16 ounces. This is real life. It just isn't going to happen. So it said that the standard deviation is set to 0.4 of an ounce. So they're saying that they're allowing the deviation, the standard deviation, or they're allowing the bags to vary by 0.4 of an ounce, which means it might be 16.4 or it might be 15.6, okay, or it could be anywhere in there, and they would consider that to be okay. Okay, so they're allowing the bags to vary with the standard deviation set to 0.4 of an ounce. Now, the quality control manager, which every big producing company has, now he's the guy that goes and makes sure that the factory is working appropriately, and their job is to, honestly, all day long, is to test the machines. So they will go in, pull bags off of the machine at any given time, and open it up, make sure the potato chips aren't crunched. They'll weigh the bags, make sure they're the right size. That's their job. So this quality control manager thinks the bags vary too much in size. So They're thinking that the bags are not as close to 16 ounces as they want. So it says a sample of 14 bags finds a standard deviation of 0.47. Test the claim at alpha equals 0.05. So he decides to pull 14 bags off the machine, weighs them, gets their standard deviation, finds that it's 0.47. Well, let's see if the bags vary too much. So when we see the word vary too much, that means our standard deviation is getting too big. Now remember, vary too much means both above and below, okay? Varies all across the board. So just like always though, we start with our hypotheses. This time though, remember we're studying standard deviation, so the variable we're going with is sigma. And in the first sentence it says, or the second sentence, it says sigma is set to 0.4. Now, the fact that this potato chip machine bags 16 ounces of potato chips, that's really not important to us. That's like extra information. So that's just telling us what we're studying, but it really doesn't affect us. We don't need that 16. It's the 0.4 we're interested in. And the quality control manager thinks that it is greater than 0.4. Varies too much, so it's greater. Now remember that the graph that goes along with this one looks like this guy, right? Chi-square looks like that. And a greater than means that we're going to be looking at a tail that's out there like that. Okay, greater than. So we're going to use our new chi-square formula, and I'll write it down here just again. So we have chi-square equals n minus 1 times s squared over sigma squared. So in our case, to find our test statistic, and this will be our test statistic, we need our n minus 1. So we had 14 bags, so our n minus 1 is going to be 13. Then we're going to multiply that by the sample standard deviation. Now be careful, the sample standard deviation comes from our 14 bags. So that's going to be the 0.47, and be sure that you square it. Don't forget to square it. Then we're going to divide by sigma squared, and sigma was 0.4. So we'll go 0.4 squared. Now, nice thing about this formula is it's like the easiest one to get in the calculator. No parentheses necessary, nothing special. So we're going to go 13 times 0.47 squared divided by 0.4 squared. And you all one step, just all the way in. And here I get 17.948. Okay, hopefully that's what you get. And you'll notice that when we look at chi-square, we also go to 3 decimal places. Okay, hold on for a second for me, guys. No, we're not playing games in here, okay? I am lecturing in here, so you guys aren't playing games. If you want to watch, you can watch, but don't make noise. Sorry, back to this. Okay, so now we're going to go to our calculator, and we're going to do the chi-square CDF. And our lower limit is this guy, 17.948. Our upper limit is going to be 10,000. And then remember, we also need our degree of freedom, which again is 13. So let me show you one more time where that is. Okay, whoop. So we're going to go second distribution, go down, 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 down. Remember, we want chi-square CDF. So click on that one. And then a 17.948 to 10,000 and a degree of freedom of 13. And enter, enter. And I got 0.1595. So remember that that thing is giving us this area, which is 0.1595. But that is also our p-value. So our p is equal to 0.1595. Okay, so now we're ready to test our claim. We had an alpha of 0.05. We came back with a p-value of 0.1595. So we were allowed a 5% chance of screwing up the problem. We came back with over 15% chance. So we didn't do all that great, did we? So we're definitely greater than our alpha, definitely, which means that we have to keep the null. And then we say, there is not enough evidence to support the claim. So remember that the quality control manager, he thought that the bags vary too much in size, did the test, comes back with there's not enough evidence to support the claim. Now, again, that doesn't mean that he's wrong. It just means that he wasn't able to do a good enough test to see that there was too much variation going on. Why is this important? Because let's think about this, okay? So if the bags vary too much, again, we talked about this, you know, you're either gonna get a full bag or an empty bag or whatever, but the company is gonna start losing money and their reliability is gonna start to fade. So, but in order to fix a machine that's bagging potato chips, you gotta turn it off, okay? So it's possible the machine has potato chip crumbs in it and it just fully needs to be cleaned. But this is a big machine, and if you turn it off, what isn't happening? We're not bagging potato chips. So if the machine is off, is the company making money? No. So the quality control manager is there to make sure that everything is running smoothly, money is being made, money isn't being wasted. So he is not, I don't know why I assume it's a he, that's very sexist of me, I apologize. He is not going to turn this machine off and have a cleaning crew come in unless he or she knows that they need to do this, that it's an absolute necessity. And honestly, the quality control manager does this every single day. Every single day they come in, this is their job, is to put together these statistical tests, run them through, decide the machine is working fine today, we'll try it again tomorrow and see what the machine looks like tomorrow. Okay, so let's see another example here. Okay, so we're talking about bolts. Let's look at the bolt machine. So this is the bolt machine. It produces bolts with a standard deviation in width of 0.05 of an inch. A recalibration was performed to lower the standard deviation. After a sample of 22 bolts were found to have a standard deviation of 0.04 inch. Was the recalibration a success at alpha equals 0.10? So it's a little bit different setup on this problem. Okay, hold on, we have a question from the peanut gallery. Yes, Ginger?
Can I go in the animal yard?
No.
No. Oh, okay.
No, go away.
Okay.
Okay. So we are producing bolts this time, and the standard deviation is at a width of 0.05, but a recalibration is done. So they decide to recalibrate the machine, which means turn it off, clean it, tighten everything, fix it, whatever. And they're doing this in order to lower the standard deviation. They want the standard deviation to be lower. After the recalibration, they sample 22 bolts and find that the standard deviation is now at 0.04. So was the recalibration a success? Okay. So we're studying just something a little bit different. In the last example, no, we hadn't turned off the machine yet. In this example, it's already been cleaned and done, and we're just making sure that everything that we did worked. So hypotheses first, as always. Remember, we're studying sigma, and right off the bat, it tells us that sigma is at 0.05 to start with, but we are hoping that the recalibration lowered it, didn't we? So we're hoping that it's less than, so we're hoping for lower. Now again, just as a visual here, because this graph is different, remember that a less than is going to be a tail that looks like this, which is a little bit different in the chi-square situation. So let's go ahead and find our test statistic. So we'll say chi-square equals, and then remember we're supposed to start with n minus 1, which in our case will be 21, times S, our sample standard deviation of the 0.04 squared, over sigma squared, so 0.05 squared. And let's see what pops out of the old calculator this time. 4 squared divided by 0.05 squared. I got 13.44. Okay, so we're gonna go to our chi-square CDF to find our area. Now remember that this is the weird one. On the low side, we've got a 0, and then up to our 13.44, and then our degree of freedom of 21. And hopefully when you stick that in your calculator, you get the same thing as me, which was 0.1076. And remember, that's that area there, 0.1076. And that is our p-value. Now, look at this one. We were allowed an error of 10% or 0.10, and look what happened. That is a real bummer, isn't it? Okay, we were allowed an error of 10%, but we came back with the probability we screwed up of being just a teeny bit over 10%. And it is actually over alpha, which means we have to keep the null, okay? Keep the null, which, remember, they already did the recalibration, which means they turned off the whole machine and cleaned it and did everything they were supposed to do. But there's not enough evidence to say that it worked, is it? So there's not enough evidence. And this one we could say to support the claim, or we can actually answer the question, because the question did say, was the recalibration a success? So we can say there's not enough evidence to show the recalibration was successful. That is a bummer. Now, why is that a bummer? Well, remember that quality control manager who's working the floor, making sure all the machines are working appropriately, it's that person's job to make sure that the company is making money. And if they turned off the machine to perform the recalibration, the company certainly hopes that when they turn the machine back on, things are working smoother and things are going better. And in this case, we can't say that. So the quality control manager in this case might be a little bit worried about their job. Okay. All right. So let's look at one more that, again, with a little bit different wording. So I'm doing 3 this time because the wording is different, because these are, they're technical, they're weird, they're not quite the same as the other ones we've seen. So this one says, an Oreo cookie press is supposed to press 1.15 inch diameter of yummy filling. The standard deviation is set to 0.011. I think, okay, apparently now I am the quality control manager. I think the standard deviation has changed in the last week. I sample, and because it's me, and if I worked at the Oreo cookie pressing plants, I sample means I would eat, okay? How many are we gonna eat? I sample 64 Oreos. Oh, that's a lot of Oreos. I think I could do it though. And find the standard deviation of filling diameter is 0.014. Test at alpha equals 0.01. Okay, so same situation here, but this time we're producing Oreo cookies, which I hope you guys all realize is far more important than the bolt machine, okay? So who cares if the bridge falls down, but if the Oreo cookie doesn't have enough of the yummy goodness on it, life is over, okay? Anyway, so we're looking at putting the white yummy goodness in the Oreo cookie. And I think that standard deviation, how much it varies in that Oreo cookie, I am just saying that I think it has changed. I'm not saying that I think the standard deviation is more or less, I just said changed. So when we go to write our hypotheses, okay, how is that affected? And isn't that going to give us a two-tailed test? So when we go for our hypotheses, our null hypothesis is going to be that sigma was set to be at 0.011, and because all I've said is changed, the only thing that I can write in there is that I don't think it's equal to 0.011. And again, that means that we need to do a 2p. Okay, so we need to look at a 2p. Now, we draw our graph here again, and it is going to be a 2p, but what we need to just decide is when we're drawing our graph, because things aren't symmetrical here, which way are we looking at? So even though that will come later, when we're looking at the graph, what I want you to notice is that 0.014 is bigger than 0.011, right? Which means that even though I said not equal, we are actually looking to the right-hand side. We are actually looking to the bigger than side. But that only comes from that number, because you can't get it from here. Okay, so from that number, then we get to say, okay, we're looking over here. Okay. Now, chi-square. So let's find our test statistic. So bigger sample here. So our sample size is 64. So n minus 1 will be 63. Our sample standard deviation is 0.014. We'll square it. And then we'll divide by 0.011 squared. And this time, what do we get? 102.050. So this is a 102.050. Okay. So and again, this guy right here is what tells us what our graph looks like, because this doesn't. So we had to look at the two guys compared to each other. And since the sample is bigger than the original, we're going to the right-hand side. Okay, so we put that in our calculator. So our chi-square CDF, we're going from the 102.050, we're going all the way to 10,000, and we've got a degree of freedom of 63. And hopefully you get, what did I get? I got 0.0013. And that's that area, 0.0013. Okay, but that's also our p-value, isn't it? So our p-value is 0.0013. But what do we want? We don't just want our p-value, do we? We need 2p. So if our p-value is 0.0013, then our 2p is going to be 0.0026. Now, luckily that's teeny, isn't it? Remember, we're allowed 1% chance. We definitely came in under that. So our 2p is less than alpha, which means we get to reject the null. So now we can say there is enough information or enough evidence to show the standard deviation has changed. Okay, remember that's all that I stated here. So that's all we can state back. We can say, well, there is enough evidence to say that the standard deviation has changed. Okay, and then remember, at alpha equal 0.01. So even the answer is technical, but remember that this is not necessarily something that we're giving to the public. This is staying inside the company. So the quality control manager has worked the problem, their statistician has worked the problem, and they come back and they say, yes, there's enough evidence to say that the standard deviation has changed. So what are we going to do? It is time, turn off the machine, clean it all out, clean any yummy goodness that is, you know, squidged into places, get it all cleaned up, and then start it up and get going again. Okay. All right, so you've seen a number of different setups there so that you are ready to go with these technical guys. And again, like I said, it's not everybody is ever going to see these again. Technical people, engineers, they're going to see this. If you're going into psychiatry or psychology, you're going to see ones that are more along the lines of, you know, working with giving people constructive criticism and different mental facilities. And if you're going into biology or something along that line, or chemistry, you're looking at more of the drug trials that come out. So there's lots of different kinds, and I'm just giving you a smattering of all of them. All right, good job.